Time to get ready for the Module 2 test. Be sure to do the practice problems listed in the module packet. Go over the review. Make sure you're ready and you remember all the different pieces, because there are quite a few different things on this test. We've got the radicals, radical functions, rational exponents, radical expressions, and then in Chapter 5, all the polynomials, add, subtract, multiply, and one of the big topics, factoring. Okay, so some few problems to get you warmed up. This one looks pretty ugly, and there's a lot of different things we need to keep track of. We've got a negative exponent and an exponent that's a fraction, so this would be a rational exponent. We could do several different things first. I like to take care of the negative sign first, so what I'm going to do first is the negative exponent means a change of position. So what was in the numerator moves up to the denominator, what was in the denominator moves down to the numerator. And so then we can write it as positive 3/2 for our exponent. The denominator of the exponent, the 2, tells us what type of root we're looking at, whereas the numerator, the top of the fraction, tells us what power we're looking at. So we've actually got a square root of 9/25 to the 3rd power. So if we do the square root first, the square root of 9 is 3, the square root of 25 is 5, and then we can cube the result, and that would give us 27 over 125. This would be a problem we could double check on our calculator while taking the test. Just be sure when you put the 25/9 in, it's enclosed in parentheses, raised to the power of, and then enclose the exponent in parentheses, the negative 3/2. And you should get something the same as what you get by hand. Next example over here, we've got some variables to keep track of. And let me move that over here. It's a little easier, a little more room. Okay. We could do this a couple of different ways. I'll kind of go at it the slow way. What I'm going to do is break everything down inside the radical to have an exponent of 4 if possible. And the reason I want the exponent of 4 is the index of my radical is a 4. And then the 4th root of anything to the 4th power will be itself. Strictly speaking, we should have absolute value signs, but I'm not going to require that on the test, as long as you can do the simplification. We'll just assume all the variables are positive. So rewriting this expression, 16 I know is 4 times 4, which is 2 times 2 and 2 times 2. So I can rewrite that as 2 to the 4th. X to the 8th I'm going to split up as x to the 4th and x to the 4th, because I know 4 plus 4 is 8. Using my properties of exponents, which you do need to remember for this test. We covered those on the first one. They come up again on the second test. The y doesn't have an exponent, so I'm going to give it an exponent of 1 just to help keep track of it. And that z to the 16 I'm going to break down. Z to the 4th, c to the 4th, c to the 4th, and z to the 4th. 4 plus 4 plus 4 plus 4 is the 16. So now anything with the 4th power and a 4th root simplifies, so I get 2 x, x. The 4th power, 4th root of y, excuse me, cannot simplify, so I'll leave that for the moment, come back to it. And then I've got 4 z's, and still stuck inside the radical is the y value. And tidying things up, I can write this as x squared z to the 4th. And a shortcut we could have used in simplifying this, going back to the original problem, 4 goes into the exponent of 8 2 times with nothing left over, and I ended up with x to the 2, and no x is left over. 4 goes into 16 4 times with nothing left over, and I've got z to the 4th with no z's left over. 4 does not go into the understood exponent of 1 on the y, and so it's still here. Okay, a couple more of these. This was kind of messy. We do have a square root over a square root, and we can combine these inside the same square root using our properties of exponents. And then I do have a 5 out here, which I'm going to go ahead and make that 1/5, move it over to the side, and deal with it later. And work with this messier part here, the 270y squared over 3y to the negative 4th. Excuse me, my eraser doesn't want to work today. There we go. Y to the negative 4 and simplify inside the radical, see what we have. So I'll have my 1/5. The 270 divided by 3 would be 90. And then I've got y to the 2 subtract negative 4. Since I'm dividing like bases, I subtract my exponent. That gives me 1/5. And 90, let's see, that'd be 2 plus 4, that'd be y to the 6th. Square root of 9, that's nice, that's a 3. And the square root of y to the 6th is going to be a y cubed. As the understood index of 2 goes into 6 3 times. And so my final answer, 3/5 y cubed. Okay, this one, messier still. I do have exponents raised to exponents. So I think on this one, what I'm going to do is go ahead and multiply those exponents. Again, using my properties of exponents, and then see if I can combine and do my simplifying with my bases. I can't combine my bases right now because I essentially have an 8th root and a 4th root down here, and those are not like radicals. So I'll clean up the exponents, make things look a little less complicated, I hope. Negative 2 times 1/8 would be negative 2/8, which of course would reduce down to negative 1/4. And b cubed to the 1/8, I can multiply those. 3 times 1/8 is 3/8. In the denominator, negative 3 times negative 1/4 would be a to the positive 3/4, and b to the negative 1/4. So now I've got some like bases that I'm dividing, and again I can subtract the exponents. So I'd have a, that negative 2/8, let's go ahead and reduce that down to negative 1/4, subtract 3/4, and then I have b to the 3/8, subtract the negative 1/4. That negative 1/4, let's make that subtract negative 2/8, changing the 1/4 to a negative 2/8. Subtracting then, I have negative 4/4 and 5/8. If when doing the problems on your test, be sure to read the directions, and you want to be paying attention to, do they ask you to leave your answer with rational exponents or in radical notations? If we wanted to leave it with a rational exponents, we are just about there. We do have a negative exponents. We never want to leave negative exponents in our final answer. So this needs to move down to the denominator. So I have b to the 5/8 on top and a to the 1, or just a in the denominator. If they want the final answer in a radical notation, that 5/8, the 8th is our index, and then the 5 is our exponent. So those are equivalent answers. It just depends what notation we're being asked to leave the answer in. Okay, so this is getting to the chapter 5 material. These first two aren't too bad. We're multiplying a monomial times a trinomial, and this one's a subtraction. So to multiply with this one, we can just do our distributive property. Remember, to multiply, you do not need like terms, but to do an addition or subtraction problem, we do need like terms. So I can multiply the negative 4y to the 3rd times the 3y to the 2nd, and just apply my properties of exponents to simplify the exponents here. So negative 4 times 3 is negative 12. Y cubed times y squared, I would add the exponents and get y to the 5th. Negative times a negative will give me a plus 4. Y. Remember, this y has an understood exponent of 1, so this will give me y to the 4th, 3 plus 1. And then again, a negative and a negative, I'll get a plus 8 y cubed. What I'm finished with here are 3 terms, so this is a trinomial. Each of these terms has a degree. This one's degree 3, degree 4, degree 5. The degree of the whole polynomial is a 5th degree polynomial, and it has a leading coefficient of negative 12. So the degree of the polynomial will be equal to the largest exponent, and the leading coefficient is the coefficient in front of the term with the largest exponent. Okay, subtracting polynomials is just a matter of combining like terms, but we do want to be particularly careful with subtraction because it's easy to accidentally lose a sign. So I'm going to go ahead and take the time to first rewrite the problem and distribute this subtraction through. So I'm going to make this plus a negative 3x and plus a positive 12. That way I don't have to worry about the subtraction anymore. I've rewritten it as an equivalent addition problem. Now I can combine like terms. I have only the 1 3x squared term, so nothing to combine there. But I do have a negative 7x and a negative 3x, so I can combine those for subtract 10x. And then the two 12s are like terms, and that gives me a 24. And the result is a polynomial with 3 terms, so it's what we call a trinomial. And I seem to have forgotten to put my exponent there. That would be important. That makes this a second degree polynomial with a leading coefficient of 3. Now we're going to multiply, and I'm multiplying here a binomial times a binomial, so I can use my FOILing method. FOIL stands for first, outside, inside, last, so it's just a little acronym to help you keep track of all the combinations you need when you're multiplying a binomial times a binomial. So taking the first term times the first term, that will give me 12m squared. My outside term times my outside term will give me a subtract 18m. Inside times inside will give me a subtract 8m. And my last term times my last term, negative 2 times negative 6 will give me a plus 12. Now I do have two like terms here. These two middle terms, subtract 18m and subtract 8m. I can combine those and have a 12m squared subtract 26m plus 12. How about if you try this one, and I'll pause a minute and see if we come up with the same result. Did we get the same result? I FOILed 3x times 4x for 12x squared, 3x times negative 5 for negative 15x, 2 times 4x for plus 8x, 2 times negative 5 for negative 10. Combining the two like terms, negative 15x plus 8, give me a negative 7x. For my final answer, 12x squared, subtract 7x, subtract 10. Okay, now we're changing directions. Now we're going to unmultiply. So this is the factoring. We've got a couple of different factoring techniques, one of which is guess and check, which I think is what I'll try on this one. My trinomial here has a leading coefficient of 1, so I don't think this one's going to be too complicated. I know x squared is going to factor to x times x. And then I can look at my negative 18 and think about what times what will multiply to negative 18. Negative 1 and 18, negative 2 and 9, negative 3 and 6. And then I'm going to take a look at my middle term here, my negative 17x. And I'm thinking the negative 1 and positive 18 look pretty promising. Let me go ahead and list a couple of these guesses out. Subtract 1 and plus 18, or x plus 1 and x subtract 18. I know both of these will give me an x squared and a negative 18. And then I'm looking for a middle term of negative 17x. So the 18 and 1 seem more promising for giving me a 17 than, say, the 2, 9 or 3, 6 combinations. So when you're using guess and check, use your best guesses first and check. So FOILing here, I'll get a negative 1x and a plus 18x, which is 17x. Not quite what I wanted. I want to subtract 17x. So here I get a negative 18x plus 1x. That does give me the negative 17x, and I know that's the correct factorization. We'll want to use a different technique on this one. I definitely have some like terms here. I'll expand it out. This might be more work than you want to do. You might want to take a shortcut, but others of you might want to go ahead and do it the long way here. That's fine. So 12 I know is 3 times 4. And a to the fourth is a. Subtract 3. A cubed is a times a times a. B squared is b times b. And then looking at the two terms, I can see I've got a 3 common to both terms and a cubed common to both terms. So I can undistribute out the like terms. This is called taking out the greatest common factor. And then leaving behind the factors that weren't common. The first term still has a 4a. I still have my subtraction separating the terms, and then a b squared left for the second term. and I can distribute back to double check my work. Okay, this one's going to be a little more challenging because I've got a leading coefficient of 3. That means there's more combinations to check out. So rather than using the guess and check method, I want to use the grouping or AC method on this particular one. To do that, I'm going to take my A and my C, the 3 and the 2, the leading coefficient and the constant, multiply them together for 6. And I'm going to look at all the different ways I can get factors of 6, so what times what equals 6, but adds up to give me a sum of -5. So 6 might be 1 and 6, -1 and -6, 2 and 3, -2 and -3. And these add up to give me -5. Now, this is not our answer. This is just an intermediate step along the path of factoring this particular polynomial. What I'm going to do with the -2 and -3 is I'm going to take my original problem and I'm going to expand the middle term, the -5x, into a -2x, subtract 3x. So this is still subtract 5x. But now I have 4 terms. And when I have 4 terms, I can use my grouping method. So I'm going to group the first pair, 3x squared. Whoops. Lost my pen. Get back there again. 3x squared. Subtract 2x. And then, just to keep track of the signs, I'm going to make this plus -3x plus 2. So looking at my first pair, I have an x common, so I'll factor out the x. That gives me 3x subtract 2. My second pair doesn't look like it has anything in common, but my goal with using this method is to get a common factor. And I can see my factors, my terms here, almost match these, except the signs are off. So what I'm going to do is factor out a -1. -1 times 3x is -3x. And -1 times subtract 2, negative times negative is my plus 2. That way, I get my common factor. Once I have my common factor, I can take it out, leaving behind x plus -1, or just looks a little tidier, x subtract 1. And then I can FOIL this back to double check. So FOILing, that would give me a 3x squared, subtract 3x, subtract 2x plus 2, and I can see I've got my original trinomial that I started with, and here is the correct factored form of that trinomial. So on the test, be sure to take the time to go ahead, multiply your factoring problems back together, double check you've got the correct result. Okay, do you want to give this one a try? I'll go ahead and pause a minute and then we can compare results, okay? How'd we do? This one had a common factor. I pulled out a 6 from both of the two terms. That left behind an x squared subtract 9. 9, I noticed, is a perfect square, so I really have x squared subtract 3 squared here. And this is one of my special forms. So x squared subtract 3 squared will factor to x plus 3, x subtract 3. A couple more. This one's kind of interesting. 16 we can think of as being a perfect square. It's 4 squared. It's also a perfect power of 4. It's 2 to the 4th. So we can break this down in a couple of steps. 16 we can think of as being 4 times 4. And y to the 4th is y squared times y squared. To get the subtract, we need a plus and minus, much like the previous problem. And then what's interesting about this one is we can factor this factor a little further because it's 2 squared subtract y squared. So this one would factor down, would still have the 4 plus y squared, and then the 4, we can factor to 2 times 2, and the y squared to y times y, plus and subtract. So this one we can actually factor down to 3 factors. And this last one, x squared plus 25, whenever you have a square plus a square, it will not factor with real numbers, and so we say this is a prime polynomial. Good luck on your test.